Hi, in the previous video, we have been discussing the priority queue abstract data type. In this video, we are going to talk about one of the most efficient implementation of the priority queues, the so-called heaps. So, let's get started. What are heaps? Basically, heap is a binary tree. So it is a tree-like structure where every single node can be two children, a left child and a right child. Of course, for a leaf node, there are no children at all. So two main binary heap types are out there, the minimum heap and the maximum heap. In a maximum heap, the keys of parent nodes are always greater or equal to those of the children. So it means that the highest key is in the root node. In a minimum heap, the keys of parent nodes are less than or equal to those of the children. It means that the lowest key is in the root node. It is complete in the sense that it cannot be unbalanced. We insert every new item to the next available place. Why is it good to know heap data structures? Because there are lots of applications, such as Dijkstra's shortest path algorithm or Prim's Yarnik minimum spanning tree related algorithm. So the heap is one maximally efficient implementation of a priority queue abstract data type. We have been discussing in the theoretical section for priority queues that another implementation could be a balanced tree implementation, but we usually implement priority queues with the help of heaps. And it's very important that it has nothing to do with the pool of memory from which dynamically allocated memory is allocated. If you are familiar with memory architecture, you know that there is a stack memory and there's a heap memory. It has nothing to do with heap memory in the sense that the heap memory doesn't have a heap as an underlying data structure. There are several heap properties to consider. It is like the AVL properties for AVL trees. It is like the red-black properties for red-black trees. Of course, we have some heap properties. The first heap property is the completeness. So we construct the heap from left to right across each and every row. Of course, the last row may not be completely full, which means that there is no missing node from left to right in a layer. For example, we have inserted the first item, it's going to be the root node. The next node we insert is going to be the left child of the root node, no matter what. It is not like binary search tree that if it's smaller than the parent node, it's going to be the left child. If it's greater than the parent node, it's going to be the right child. We are going to build the heap data structure so that it's going to be complete. So we have the parent, then the left child, then the right child, then the left child and right child for the left child, then the left child and right child for the right child of the parent, and so on. So the next node is going to be like this. The next node is not going to be like this because it's not going to be complete, because this node is missing a right child and this node is missing a left child. So we are not able to consider this structure as a heap if we allow this right child here. So that's why we have to insert the next item here. Okay, then like this, then like this. So this is why I said that it's going to be complete. We have to construct heaps on a line-by-line basis from left to right. We have the root node, then the left child of the root and the right child of the root. Then the left child and right child for the left child of the root. Then the left child and right child for the right child of the root, and so on. We go on a line-by-line basis from left to right. Otherwise, the heap would be incomplete, which means that it's not going to be a heap data structure. So like this and so on. So again, it's not going to be a heap because it is not complete because of this node with the value 20. So again, the heap properties, it's going to be complete. So there is no missing node from left to right in a layer. Then, in a binary heap, every node can have two children, a left child and a right child. In this sense, it is very similar to what we have seen for binary search trees. Every single node can have a left child and a right child. But it's extremely important that we do not state that the left child is smaller and the right child is greater than the parent, as we have done for binary search trees. For heaps, We just have to define that every single node has two children, left child and right child, but we don't specify whether the left is going to be greater or smaller than the parent. It doesn't matter. What's very important that for a minimum heap, the parent is always smaller than the values of the children. For a maximum heap, the parent is always greater than its children. So it's very important that the children, the left child and the right child, has nothing to do with each other in the sense that we are not able to define that the left child is greater or smaller than the right child. What's very important that the parent is greater than its children for a maximum heap. For a minimum heap, the parent is smaller than the values of its children. Why is it important? Because we know for certain that the root node will be the smallest or the greatest value in the heap. Of course, it depends whether we have implemented a minimum heap or a maximum heap. Why is it good? Because usually for applications such as shortest path algorithms, we are looking for the smallest distance possible. Then we construct a minimum heap and we are going to take out the edge between two nodes in the graph with the smallest value possible. And because we have constructed a minimum heap, we know that the root node is going to be the item we are looking for, so the item with the minimum distance. So we are able to access it in order 1 constant time complexity. This is why it's good to use heaps. So for a maximum heap, the greatest item of the tree-like structure is the root node. As you can see, the root node is greater than its children, 7 and 10. But as you can see, it doesn't matter whether the 7 is the left child or the right child. What's very important that the parent always has to be greater than its children. And it is a valid heap because the parent is always greater than its children. So that's all about the maximum heap. For a minimum heap, the root node is going to be the smallest item possible. As you can see, the parent is always smaller than its children, 12 and 23. But it doesn't matter whether the 12 is greater or smaller than the right child. It doesn't matter. It's not like binary search trees. We could have the 23 as the left child of the parent and the 12 as the right child. Of course, we have to make sure that the parent is always smaller than the children for a minimum heap. For a maximum heap, the parent is greater. For a minimum heap, the parent is smaller. As you can see, 12 is smaller than 22 and it's smaller than 15. 23 is smaller than 56. Okay, so it is working fine. Okay, so that's the main difference between a maximum heap and a minimum heap. Why is it good? Because the minimum item or the maximum item will be the root node, and we are able to access the root node very fast, order 1 constant time complexity, and most of the times it can have useful applications. Thanks for watching.